Hi, my name is Gabe Kronson, and I'm going to be presenting a data analysis on transient event light curve decay. So for a little introduction, our question was, can gamma ray / X-ray data from black hole binary neutron star mergers and magnetars be fitted into an equation to determine and analyze parameters in order to differentiate between transient events? So for a bit of context, thousands of catalogs and data repositories with easily accessible data points are available online, which is where we drew our data from. Our goal was to make a system to differentiate between different transient events, which would be very important for future data analysis, as it makes a way for analysis without using spectroscopy, which often can be very expensive. This is generally a basic experiment. Much more advanced systems have been already created, but it is still very important for the records and for literature. So the difference between recurrent and transient events, just for clarification, is that recurrent events are ones that occur repeatedly in a pattern. Um, they generally have a probability of occurring over again, and this probability decreases over time. Transient events, on the other hand, are events that occur only once or last a short time, similar to an explosion. Gamma ray bursts, magnetar flares, and kilinovae fall under this category. The shapes are very similar between recurrent and transient events, and recurrent events can be separated into individual transient events. All right, so gamma ray bursts, or GRBs, come from black hole engines that serve as progenitors. Electromagnetic radiation is emitted from the engine, sending gamma frequency light waves in two directions. These waves spread out, eventually colliding with material ejecta in the surrounding space and forming an afterglow. So the main difference within gamma ray bursts is between long and short gamma ray bursts. Long gamma ray bursts are more common, where the time of 90% of the gamma ray burst is greater than 2 seconds. These originate mostly from supernovae, and they have a high luminosity. The concentration of gamma rays is therefore much lower, and it's spread over a greater amount of time and space. Short gamma ray bursts, on the other hand, are less common. It's when 90% of the gamma ray burst is between 0 and 2 seconds, generally. These originate from black hole binary systems and are dimmer in luminosity by about 10 times than long gamma ray bursts. However, the concentration of the gamma rays is much higher for the short amount of time that it is present. So an afterglow is what it means, an afterglow after the initial gamma rays have subsided. The gamma ray bursts are still observable at higher wavelengths, meaning more energy. Long gamma ray bursts have longer afterglow phases, while short gamma ray bursts afterglow phase is much shorter, obviously, almost instant. It shifts as the blast collects material surrounding the event, which can be physical matter or colliding with other energy sources. Visible light does not always exist in the afterglow of all gamma ray bursts, and this is the portion of gamma ray burst that is studied. And so here is the electromagnetic spectrum. So there's an inverse relationship between wavelength and energy. And so gamma ray bursts, which have very low wavelengths, have very high amounts of energy. And as it goes into an afterglow phase, it loses its energy, which means it gains higher wavelength. Magnetar flares are the most highly magnetized neutron stars. They form in a different way than other progenitors for gamma ray bursts. They are about 1,000,000,000,000 times stronger than the magnetic field of Earth. Magnetars rotate about twice as fast as normal neutron stars. The fastest ones get up to about 1.4 rotations per second. The magnetic field is constantly shifting, and the transient event of magnetars is called giant magnetar flares, or GMFs. These are rare eruptions called flares and another form of gamma ray bursts. Magnetar flares also have an afterglow phase in which the energy decreases and wavelength increases, which can be analyzed similar to gamma ray bursts, and is almost identical. These are mainly extragalactic, and there are only 3 in the Milky Way. Kilinovae are similar to nova or supernova. They are about 100 times more powerful than a nova and about 10 times less powerful than a supernova. They're caused by binary neutron star mergers, BNSM, which are two already dead stars that collide, sending gravitational waves through space-time. Generally, events like these only produce gravitational waves, but kilinovae in particular have electromagnetic components that allow for gamma ray analysis as well. They produce both ejecta and electromagnetic radiation in the form of gamma rays like the others. Um, And very similar to the others, they have an afterglow phase that lasts for less than a second. And what makes them different from other gamma ray bursts is the angle of ejection. The angle of ejection is a little bit different. Light curves and decay. So light curves are analyzed with the use of X-rays, which are higher wavelength and lower energy than gamma rays. Gamma rays decay very quickly, and X-rays follow in the afterglow of transient events after it's kind of slowed down and used some of its energy. The decay of X-rays is what is used to analyze light curves. Thousands of points of data um, exist in X-ray luminosity. Uh, for our experiment, we use the Swift X-ray telescope, which is a spectrometer that measures position, spectrum, and brightness of gamma ray bursts and afterglows. It allows for the data collection of long and short gamma ray bursts. For magnetar flares, we use the Magnetar Outburst Online Catalog, which is a data catalog that contains luminosity versus time graphs for magnetar flares that's already ready for analysis. For kilonovae, we used a data set by Kei Mukai, which is an article by a well-known astrophysicist that samples data from kilonovae. And the energy band, which we performed our experiment, was in the general range of 0.2 to 10 kilo electron volts. And so a light curve in our experiment is defined as a graph showing the brightness of an object over a period of time. For example, comparison of luminosity versus time. Um, Luminosity is the magnitude of flux passing through a certain area, or the measure of the brightness of an object or light as amount of energy per second. Luminosity is measured using ergs per second in our experiment, which is a much smaller unit of energy compared to joules, which is another standard unit of energy. Light curves and their decay are valuable when studying gamma rays, as they provide a visual representation of the electromagnetic spectrum on a graph. Um, and lastly, it's a more photometric approach to analyzing transient events, which means it does not require the position or distance of the event, only data tying back to the spectrometer point, in which it's generally very expensive. And so a photometric approach would be very beneficial. On to the actual experiment, we used Python data sets and fitting with power laws. So power laws are very common mathematical relationships that are used to fit data. They're both numerical and graphical representations of a trend of decay. For ours, we used the function y equals mx to the power of b, and it's able to be scaled. The parameter b shows the steepness of the decay. We use coding language Python in order to process the data, analyzing 55 different light curves. We had 15 short gamma ray bursts, 21 long gamma ray bursts, 4 kilonovae, and 15 magnetar flares. Each dataset was processed by hand through Excel and exported through a CSV file. Using the SciPy curve fit argument in Python in order to fit the data to the power law y equals mx to the power of b, we were able to fit each of the data sets. And just looking at them visually, they're all different, looking at the keys here. This is an analysis of residuals to determine the accuracy of the line of best fit using Python. Generally, they are pretty accurate based on the scale. The mean deviations are obviously a little bit different depending on how much deviation each graph has. And so the results of our experiment, after fitting each of the data sets, we were able to extract the list of values for B and actually calculate values for B in the power laws that show the steepness of the decay. And so this was calculated by appending all of the values of B from the curve fit function across all of our data sets into one single value. And so each transient event has a different decay pattern that is unique. So looking at this graph here, we have use box and whisker plots to kind of graphically represent our data to show that each of the factors of decay varies depending on what kind of transient event you're looking at. And comparisons to literature. This experiment has been done before, but many use double or triple power laws, so ours is much simpler. We have a benefit of using photometric analysis to differentiate light curves, which does not require distance. It's not new, but it is generally not used to differentiate between transient types, and spectroscopic analysis is more commonly used, especially with the Swift X-ray telescope, but then again, that is very expensive technology that is very limited. The most accurate results from our experiment in comparison were the short and long gamma ray bursts. in comparison to other literature. Our experiment could have been done in many different ways, including fitting more light curves, which would have resulted in a much more accurate data set. Our data set of 4 kilonovae could have used more points of data. Different power laws, more accurate light curves. We could have included double or triple power laws like much of the literature does. We could have included different kinds of transient events and included broken up recurrent events if we wanted to as well. So our conclusions for this is obviously an impact. So thousands of catalogs and data repositories within easily accessible data points. Once again, we are trying to make a system to differentiate between transient events, which is very important as it allows for the easy and efficient processing of data that is being thousands of data points are being collected every day, and an easy, efficient way to organize these data points is very important. It makes way for analysis without using spectroscopy, which is generally more expensive. And our results, we were able to differentiate transient events using only luminosity and time. And by finding the magnitude of the decay, we could determine different properties about the decay as well, in addition to differentiating them. Here's my image credits. Thank you for listening.